All right, this is a debrief for orbital mechanics homework 5, circular, elliptical, and Hoffman orbits. Number 1, satellite orbits Tantalus 5, which is from Star Trek, the original series, at a constant altitude of 758 kilometers above its surface. Tantalus 5 has a diameter of 27,500 kilometers and a mass of 5.55 times 10 to the 25th power kilograms. Calculate the orbital period of the satellite and express your final answer in units of minutes. Little diagram. We're given the diameter, so of course the radius would be half of the diameter, and we're given the altitude, so the orbit radius, r, is going to be the planetary radius plus the altitude. And to calculate orbital period, we can use the formula t squared equals 4 pi squared r cubed over gm. So in this situation, we take 27,500 kilometers divided by 2, then add 758 to that, and I get 14,508 kilometers for R. Well, so 4 pi squared. Now I have to turn kilometers to meters, so 14,508,000 cubed divided by G divided by 5.55 times 10 to the 25th power. And there's my answer in seconds, but I want the final answer to be in units of minutes. So divide this by 60, and I have a period of time of 543,000 minutes. Interesting. And that's because I forgot to take the square root of everything. So this is wrong. Multiply by 60. And first take the square root of everything. Then divide it by 60. This is a much more reasonable result. 95.1 minutes. Number 2, a second satellite also orbits Tantalus 5. This second satellite is moving at an orbital speed of 3.14 kilometers per second in a circular orbit. Calculate its orbital radius. Well, for this one, I use v squared equals gm over r, and I'm rearranging the equation to solve for r. So r is equal to gm over v squared. In this case, alpha g times 5.55 times 10 to the 25th power divided by, but of course I have to express the velocity in units of meters per second. So 3,140 meters per second squared, enter. There is my orbital radius in units of meters. I would prefer to express it in units of kilometers. So dividing it by 1,000, I have an orbit radius of 376,000 kilometers, a reasonable value. Number 3, an Orion spaceship is in elliptical orbit around the asteroid 6 Hebe, which is a real asteroid. This asteroid has a mass of 1.27 times 10 to the 19th kilograms, diameter of 186 kilometers. If the Orion spacecraft is at a periapsis altitude of 50 kilometers above the surface and an apoapsis altitude of 325 kilometers above the surface, calculate the semi-major axis, and so forth. Well, so I have to take, again, the radius of this asteroid is half of its diameter. So what we have here is, I would prefer to add the radius to each of these separately and then do the average, although mathematically that doesn't matter. So if I go 186 divided by 2, I have an orbital radius of 93 kilometers. So if I go 93 plus 50 plus 93 plus 325, divide that by 2, that gives me a semi-major axis A of 281 kilometers. The orbital period, t squared equals 4 pi squared, in this case A cubed over gm. So if I go 4 pi squared, answer, let me back that up, close parentheses, answer times 1,000 to convert it to meters first, then cube it, then divide it by g, then divide it by the mass of 1.27 times 10 to the 19th power. This time, try to remember to take the square root. There's the orbital period in seconds. 32,100 seconds. And not required, but that is equivalent to 534 minutes or 8.91 hours. Not required to do the conversions, but sometimes it's convenient in your mind to say, oh, okay, that's how much time. For periapsis velocity, I would calculate the average velocity first using the semi-major axis, using v squared equals gm over a. So the square root of alpha g times 1.27 times 10 to the 19th power divided by the semi-major axis was 280,500, as I recall. Enter. The average orbital velocity is 55.0 meters per second. Now to get the periapsis velocity, I multiply this by the ratio of the apoapsis radius divided by the periapsis radius. So if periapsis is closest, it's going fastest, so you want the bigger number over the smaller number. So multiply this by the square root of, and I didn't write those things down before, so 93 plus 325 over 93 plus 50. And I have a periapsis velocity, so part C, of 94.0 meters per second. For the apoapsis velocity, if I were to take the answer and replace it with 55.0 and then divide this instead of multiplying it, well, basically, I should just re-enter this. Okay, 55.0 divided by, or never mind, 55.0 times the square root of, and this time I put the periapsis radius on the bottom. So 93 plus 50 over 93 plus 325. and I have an apoapsis velocity of 32.2 meters per second. Number 4. A Dragon spacecraft is in a circular orbit around 6 Hebe, same satellite. Its altitude is 45 kilometers above the mean surface. The crew decides to undergo Hoffman transfer to a circular orbit with an altitude of 315 kilometers above the mean surface. Calculate the inner orbital velocity and everything else. Well, I'm going to do this all in one shot because I have a program that answers all these questions. But to tell you how to get it, for inner orbit velocity, you have to again take the altitude and realize that the orbit radius is the sum of the mean radius plus the altitude. And then to get the circular orbit velocity, v squared equals gm over r. Same thing for the outer orbital velocity using the second altitude. To calculate the average orbital velocity, you would use v squared equals gm over a, the semi-major axis. Periapsis velocity would be the average orbital velocity. So your answer from C times the square root of the apoapsis radius over the periapsis radius. For the apoapsis velocity, it's going to be the average velocity times the flip of this. So the periapsis radius over the apoapsis radius. Delta V, change in velocities. So V peri minus V inner circular orbit. Outer one is going to be V of the outer orbit minus V apo. Total delta V is the sum of F and G. Your answer from F and your answer from G. Time of flight is going to be 1/2 the orbital period. So you still have to do T squared equals 4 pi squared A cubed over GM. And then time of flight is half of that period. Okay, well, I'm just going to run a program to do all those calculations for me in one fell swoop. So my program is called Orbit, and my central body is going to be other than one of the ones we normally have. Its mass for 6 Hebe is 1.27 times 10 to the 19th power. And the radius of this, it says its diameter is 186. So if I take 186 and divide it by 2, it'll give me the mean radius, which you can see is in the range of typical asteroids. A little feature I added to my program. I'm going to do a Hoffman transfer, and I'm going to enter the 2 radii. So the first one is the radius of the body plus an altitude of 45 kilometers. The apoapsis radius is the radius of the body plus an altitude of 315 kilometers. So here's all the answers. The inner orbit velocity is 78 meters per second. So there's the answer to part A. The outer orbit velocity is 46 meters per second. The the semi-major axis wasn't asked for, but there it is with its period. The average velocity, so this is the answer to part C, The answer to part C is 56 meters per second. The answer to part D is 96 meters per second. The answer to part E is 32 meters per second. The answer to part F is 17 meters per second. The answer to part G is 13 meters per second. The upper one is always going to be less than the inner one. And then finally, part H, the total delta V is 31 meters per second. And part I, total time of flight, is 15,394 seconds. Yeah, I tend not to round that one off to 3 sig figs like you should. Okay, so if I take that 15,394 and I divide it by 60, this corresponds to 257 minutes, which is a little over 4 hours, 4.28 hours. Ta-da! This ends the debriefing on this assignment.